Okay, so we're calling this net area under the curve. I mean, I drew it with all positives here, but could have some negatives, negative area rectangles, if you will. And so this net area under the curve is, it's approximately that we call it a Riemann sum also. It's approximately the sum of all the delta x's times the f of x of I. And I use right-hand endpoints here, but we can use midpoints. And so, again, sometimes they just use a little star there to denote. Pick one, right-hand endpoints, midpoint, something. But you could use several options here, or several options here. That approximates, and I here runs 1 to n. That approximates it. Well, what I want to talk about now, though, is I want to get it more precisely. I want not an approximate, but I want a precise, equal, exact area. Well, the way I can get this to be precise, because yeah, if you just use rectangles, you're always going to have a little bit overage or underage on each rectangle. Well, to get it precisely, we talked about this a little bit last time, if I could do infinitely many rectangles, because 1,000 rectangles, that puts, just a small amount of error in. So if I could do infinitely many, though, I could get rid of that. And so here's how I do that. If I take and run in, make it 1,000, make it 1,000,000, if I could do this. Let n run to infinity. So basically what I'm doing is doing a limit as n goes to infinity, making that n larger and larger and larger. That will give me precise, exact, exact net area. If I could do that somehow, some way. None of this approximating business, okay? That's precise. Equals. Well, as you can probably tell, this little thing right here, that's a pretty big deal. And so, for that reason, among others, it's given a name. It's called the definite interval. So this is the definition of the definite interval. So if f is continuous, for x between a and b, then the definite interval of f from a to b is this. First of all, the notation. It's the integral symbol. You haven't seen it before. It's kind of a elongated, narrow S-looking thing. Your endpoints, the A goes here, kind of a subscript, and the B goes kind of a superscript on it. That's where those go. The function that you're integrating, doing the integral of, is in here. And then we also have, we're bringing back another thing, it's the differential dx. That goes in here too. That, we'll talk about what that means here in a second. So that's the notation for what's called a definite integral. And what does it equal? Turns out it equals this thing we just talked about. The limit as n goes to infinity, summation I equals 1 to n delta x, let's write it this way. F of x sub I star times delta x. Now you kind of see some correlation here between the two sides, right? You got dx and you got delta x. Remember, dx equals delta x? So you kind of see where that comes from. There's more what it means here. I'll talk about that in a second. And then, of course, you got your f of x, you got your f of x. So I guess more or less what you can say is this integral from a to b, that's this part of it, if you will, right? The integral is this limit as n goes to infinity of this summation stuff. You see what I'm saying? But that's the definition. So what is really, truly, definition-wise, what is an integral? It's infinitely many rectangles. Okay, that's what an integral is. A definite integral. Infinitely many rectangles. It's a nice, in a lot of ways we've learned it's really nice, if you don't already know, but it's just a nice way of writing infinitely many rectangles. These Riemann sums. All right. We already talked about the symbol, that's the integral sign. The a and b, typically on an integral, what you call those is your upper and lower limit. A is the lower limit of your integral, and b is your upper limit. The f of x, that's your integrand. Another term we don't use a whole lot, or I don't typically use it a whole lot, but that's what it is. It's the integrand. And then the dx, why do we have the dx? Well, for one thing, it goes along with the delta x, but what that also tells you is what you're integrating with respect to. That's one of the purposes of this dx. It tells you what you're integrating with respect to, whether you're integrating with respect to y, or x, or z, or whatever variable. That's one of the purposes of that dx, is to tell you, because sometimes it may vary. That tells you what you're integrating with respect to. Okay. All right. So that's the definition. What do you see? What does it graphically mean then? What is an integral? If I drew y equals f of x here, let's do this one first. Here's a and here's b. And I ask you to label this quantity here, this expression. What does that represent over here on the graph? It's that, isn't it? It's the net area under the curve, between the curve and the x-axis, however you want to say it. So what we're saying is, the integral here is this area right here. Okay? The integral equals an area. That's what an integral equals, an area. Now, area, that can kind of get you in trouble, because what if your function does this? Here's a, here's b. So what the integral there represents, well, it's this area, and then this area. But then what happens with this area? You got a negative, don't you? So you got a positive, and then you got a negative, and then you got some more positive area. And so you're adding some, you're subtracting some. So again, it's a net area between the curve and the x-axis. that's what the integral represents. But its area, that's what integral represents. Okay? Okay. So with this new definition, if you will, we'll deal a little bit with the definition. Not a whole lot. We will do some work with that. But for now, here's what we're going to do. Back to the handout I gave you there. 2A. Let's click on 2A now. About 10 there. This is about a 4. Something like that. Okay. Hold on. All right, so let's estimate for this function integral 0 to 6 f of x dx with 4 subintervals and right-hand endpoints. Okay. So I want to estimate that interval. What is it I'm estimating? Well, I'm estimating the integral from 0 to 6 so 0 to 6, I want to estimate the integral. Well, the integral, what's the integral? The integral is the area under the curve. So I want to do that with 4 subintervals and right-hand endpoints. This is the same thing we've been doing. We're just now calling it estimating an integral instead of approximate the area between the curve and the x-axis. It's the same, very same problem that we've done before. Our delta x here is b minus a over n, so it'd be the a and the b here. That's the a and the b, 6 and the 0. N is 4, so I'm talking 6/4, which is 1.5. We use right-hand endpoints. So here's what I've got. So first when I go to 1.5, start at 0, go to 1.5. Using right-hand endpoint, so that one's going to be that. So it looks like it's approximately mine's a little bit off. This should be a little bit higher. 10. Should be around about 11, I think. So the integral here is 0 to 6 f of x dx is approximately equal to 1.5 is the width, and then the height is about 11. It's the same thing we've been doing, just getting that delta x and then multiplying it by the heights for each one. Since I don't have the function here, I'm just estimating it off the graph. So the next one will be at 3. So what have I got at 3? Well, it looks like at 3, it's up there about 5. For the height. The next will be at 4.5, which at 4.5, yeah, I'm on the negative side, that height there, be a negative. I'll call it a negative 3. And then last but not least, the last one would be at 6. So that height there is about, let's go to negative 9. So about a negative 9 there. With me? All right, so 16 might as well 4 times 6. I get that into about 6. It'd be about 6. If you do all the calculations there. So, okay? Believe that? The second one, 2b. So let's estimate 0 to 6 f of x dx with the midpoint rule. N equals 4. So it's the same integral, except now I'm using midpoint rule, so I'm going to use midpoints instead of right-hand endpoints. So the integral here is same delta x, 1.5, same delta x. But I'm using the midpoint rule, so instead of going up at instead of going up at 1.5, I would go at the midpoint there, which that'd be about 0.75. So I'd go up at 0.75 to get the height of that rectangle. So about 0.75. That looks like it's about 10. Still 1.5 wide, but the height now is 10. All right, then, oops, too far over. All right, so then the second one is 1.5 to 3, but I would go at the midpoint between 1.5 and 3, which between 1.5 and 3, let's see, 0.75, 2.25. So go up about 2.25 for get your height there. Which that's, I'm going to call about 9. The third one, so it'd be between 3 and negative 3 and 4.5. But the midpoint between 3 and 4.5 would be 3.75. So that's actually going to give me a positive value, I think. 3.75. I'll call it 2 for the height there. So at 3.75, go up there, I get a 2. And then between 4.5 and 6, midpoint there. What is the midpoint? Probably should have wrote them out so I wouldn't have to calculate every time here. 3.75, so 5.25. That's going to be a negative, of course. So a negative 5.25, and let's say it's -6. Yours could be slide off that. So that I think it is -6. All right, so yeah, that gives me a little bit different, but using midpoints. $34.5. Yeah. 34.5. Are they different? Is that all right? Any questions or concerns on that? Okay. Now, maybe that's what I did. Okay. And if you flip over here, what we can do in some cases, so this is 3A on the handout. If our function is made up of line segments instead of curved lines, here's what we can do for integrals in that case. So 3A, let's do the integral from 0 to 4 f of x dx. So what I'm going to do is I'm going to calculate this integral by interpreting it not with rectangles, but in terms of area. So I'm going to calculate these integrals by interpreting it as an area. And like I said, I can do these on ones like this using an exact area. Here's what I mean. So in this case, I went 0 to 4, which 4 is right here. And so the integral I'm talking about, it's this area, isn't it? It's the area under this curve. Well, that area, there's 3 parts to it. Because it's straight lines, there's 3 parts to this area. I got a rectangle, and then I've got a triangle, and then a bigger triangle. So let's call this 1, 2, 3. Number 1 is, like I said, that's just a rectangle. This happens at 2. It's a little bit off. 1, 2, 3. So that first area there is just a rectangle. It's a 2 by 1 rectangle. So the area of it's 2 times 1. The second area, it's a triangle, so it's 1/2 base times height. The base is 2. The height is 1, 2, 3 units long. So that area is calculated by, this is number 2. Just doing the triangular formula, 1/2 base times height. It's 1/2 times the base, which is 2, and then the height is 3. You with me? What's the third one? Another triangle. It's 1/2 times the base, which again is 2. And then the height is 1, 2, 3, 4. It starts from here on up. So it has a height of 4. So that area would be 1/2 of 2 times 4. So what's that? 2 plus 1/2 of 6 is 3, plus 1/2 of 8 is 4. So this area is 9. So this integral, 0 to 4, is not an approximation. It's an exact value. It's 9. It would be that area. Okay, we do number 2, 2b. For 2b, let's go from 2 to 8. 2 to 8. Yeah, 2 to 8. Well, you got the same shape. But I'm going from 2 to 8. So what have I got there? Well, it looks like I've got this triangle, and then I've got another triangle, a small little narrow one right there. So again, I've got 3 areas. So number 1, I think we just did that one, but it's 1/2 base times height would be 1/2. The base would be 2. The height is 4. So yeah, that's the we did a while ago. But what about this number 2 area, the one in the triangle in the middle there? Well, it's also a triangle. So it's a 1/2 base times height. The base is 1, 2, 3 though, isn't it? It goes from 4 to 7, so the base is 3. But what's the height? Well, the height you can get right here at the 6. You go there to that point. That would be the height, which that goes all the way down to, oh, I guess I didn't make it. Did I? It may be slightly off -4, maybe -4, maybe slightly. But the height is negative, is whatever we choose there. That's going to give me a negative answer. And then the third one is another triangle, so it's 1/2. The base is just 1. The height is 4. Let's go all the way up there at 4. So the base is 1, the height is 4, so area is 1/2 times 1 times 4. So here's what I've got. I've got 8, half of 8, which is 4. Half of -12, which is -6, and then half of 4, which is 2. Oh, how about that? That gives me 0. What does that mean? Well, that means I've got this area and this area counteract each other. I got the same amount on the top as I do on below. Anyway, so those you can do that way. Now, got one more little piece here. Is that okay? Any problems or concerns? All right. Now, kind of in a similar fashion, we can do a couple of other integrals, and then we'll really open it up next time. Let's evaluate these integrals again by interpreting them as areas. Number 1. The integral 0 to 5, 2x dx. And we'll talk about how we'll actually do this one in much more fine detail, not too distant future. But if I interpret this as an area, I can go ahead and do this integral because here's my function, right? That's f of x. So if I graph f of x equals 2x, here's what I've got. Right? That's what that line looks like, something like that. So what's the integral 0 to 5? Well, it's this area right here, isn't it? Whoa, that's steep. Isn't it this area right here? What is that? It's a triangle, right? So that's 1/2, the base is 5, and then all I have to do is figure out the height, which is just that y value at x is 5, wouldn't that be 10? Wouldn't that value be 10? So it's half of 50, it's 25. Okay? Now later on that won't be how we do it, but we could do it this way. Now here's another one. Same thing. This one actually is a tougher one to evaluate in different ways other than this way that we're talking about. It's really not that bad though. Because what I have here, if again, this is my function, and maybe you don't recognize that. Oh. Maybe you do, but does anybody recognize that? What shape that is? I mean, if you graph it on your calculator, it'll kind of give you a distorted view of it, but it's a semicircle. It's half a circle. Radius is 4. Center at 0, 0. Yeah. Square root of 16 minus x squared is a semicircle radius 4. All right. The question though was, what's this integral from -4 to 4? Well, I'm talking about this area right here, aren't I? This integral is the area under the curve. So I'm talking about that area. Now, interpreting it as an area, I can figure out this integral because I know, well, a circle's area is pi r squared, right? So a semicircle would be half of that. 1/2 pi r squared. So this integral is going to be 1/2 pi times the radius squared. So it's 1/2 pi times 16, which is 8 pi is probably how they'd write that. Half is 16. Okay? I got you one more because of what they'll give you on the homework. This will be the last one. All right, so you've got 0 to 3, integral 5 minus the square root of 9 minus x squared dx. Well, what I have to, and we'll talk more about these properties later on, but what I need to tell you is that if I've got two functions, a to b f of x plus g of x, if I've got two functions added together, good news, that does equal the integral a to b of f of x plus the integral a to b g of x. Now in this case I have minus, but it also works in the case of minus as well. So you can do that with addition and subtraction. You can separate those integrals they separate and you can do them separately. Why do I say that? Well, if I interpret these as areas, here's what I've got. So with that fact, says I can separate these two into two separate ones. So now I can do 0 to 3 of 5 dx, and then minus the integral 0 to 3 square root of 9 minus x squared dx. See what I'm saying there? Separate those into two separate integrals. Now I can look at these areas separately. This one, I've got f of x equals 5 or y equals 5. That's just a horizontal line, isn't it? Through 5. That's what that graph is. What's the integral? 0 to 3. It's that area from 0 to 3 under the curve. What is it? It's a rectangle, isn't it? A 3 by 5 rectangle. So this area is 3 times 5. That integral is 3 times 5. Now what about this one? Well, this is f of x or y equals square root of 9 minus x squared. Well, we just talked about a similar one. It was 16, the square root of 16 minus x. What is this one? Wouldn't that be a semicircle, radius 3?